So let's do a recap of our ionic bonding and our covalent bonding and the bonding unit. All right, so in ionic bonding, a metal transfers electrons to a nonmetal, right? So a transfer means that the metal is going to lose electrons, and then the nonmetal is going to gain electrons, right? Because we have a transfer means one gives, one takes. Remember, transfer, ionic, covalent, share, ticks. All right, so the properties of ionic bonds, right? So you really should know these properties because you should be able to identify the type of bond based on the properties that were given in a question. So if it is a rigid crystalline structure, a high melting point and a boiling point, so you may also be given numbers like this, and if it's a high number, it's a high melting point and boiling point. If you have a negative number, that's going to be a very low melting point and boiling point. And conductivity in the liquid and the aqueous phase, because that is the definition of an electrolyte. So not a solid phase, so not as a solid. So what I'm telling you is you really need to pay attention to the phase. So if you see a little s, that's going to not be conductive. If you see an L, that's conductive. And if you see an AQ, then it means that it is conductive. So ionic bonds are conductive in the liquid or the aqueous phase because they have what we call mobile ions. Right, so that means the ions are free to move, right, which is an electrical current because a current means movement. So that's our ionic bonding. And remember, where do I find the metals and the nonmetals on the periodic table? Metals are on the left-hand side of the periodic table. Nonmetals are on the right-hand side of the periodic table. And don't forget hydrogen. So hydrogen. Okay, now let's move on to our next type of bonding recap. And so now we have covalent, right? So the prefix co means share. And what are they sharing? Valence electrons. So we're going to have the opposite of our ionic bonds. So we have only nonmetals. So exactly everything to the right on the periodic table. And then, of course, hydrogen over on the left. And it shares electrons with another non-metal, so two non-metals, right? So transfer, ionic, covalent, share, ticks. So if they're shared equally, it is a non-polar bond. Whenever you see the word bond, you want to say which elements are getting together. And if they're the same element, non-polar means not different, which means the same, right? So then that's going to be our Brinkelhoff, or Hofbrinkel, whichever way you like to say it, or 7-Up, right? Those are our diatomic elements on our periodic table. Take a peek over here at our periodic table, right? What I mean by 7-Up, there's 7 of them. They form the number 7 over here, right? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and up, which is going to be our hydrogen up here. So those are your diatomic. Those are non-polar covalent bonds because they are shared equally. So because they have the same electronegativity value, so the same electronegativity. Now, if we're shared unequally, it's a polar bond. Remember, a bond is which elements are getting together. Polar means different. So if I have two different nonmetals, so I'm just going to do a non-M, right, for metals. So two different nonmetals, and they have different electronegativity difference. Or sorry, different electronegativity values. And then here we have our properties of our covalent bonds, which are exactly opposite the properties of the ionic bond. So soft solids, gases, and liquids, whereas the ionic bonds were hard crystalline solids. Low melting point and boiling point. Ionic had a high melting point and boiling point. Insulators means non-conductors. That means they do not conduct at all, solid, liquid, or gas, or aqueous, right? Covalent is non-conductive. So then also we're non-electrolytes. So they're non-electrolytes. If you see something that says the most or the least polar, or most or least ionic, you need to go to table S of your reference tables, and you need to find your electronegativity values, and then you need to subtract them because it's going to be electronegativity difference is going to tell you. And if it's the most polar, if you're given 4 things and you need to figure out which one is the most polar, the one with the largest electronegativity differences, right? Difference means subtract electronegativities from table S. And if it's going to be the most ionic, you're going to have the largest electronegativity difference. So most or least is going to be either largest difference or smallest difference, right? Use those electronegativity values. So now let's talk about our metallic bonding. The metallic bonding is what we have that's within pure metals. And we have that sea of mobile electrons, right? So the mobile electrons is why metals conduct electricity. So if you see something that's a solid and it conducts electricity, you're going to have yourself a metal. So it's the only ones that solids can conduct electricity. They can conduct electricity in any phase because their electrons are free to move. In an ionic bond, right, when they dissolve in water or they're liquefied, then the ions are free to move, and then they will conduct electricity. Metals don't bond with other metals, right? So we have our properties of the metals. We have malleable, right? So that's our fancy word to mean it can be shaped. Ductile, our fancy word that means it can be drawn into wires. Luster is our fancy word for shiny, shiny, pretty. High melting point, but lower than ionic. Right? And so that's going to be the recap of our 3 types of bonding. So now network solids, not tested on the Regents exam, but we'll just go over that really quickly, right? So we have a network solid, crystalline, rigid structure, but it has a covalent bond instead of an ionic bond. High melting point, boiling point, silicon dioxide, which is sand, SiO2, and diamond are the 2 examples of a network solid. So I do want to go back and let's just quickly, oh, hold on. I want to go quickly backwards. Sorry, guys. From current slide here. Oh, see, I messed this up. All right, let me go back over here. And I want to go back to our, where do I want to go here? All right, so let's just go back here to our network solids. And I don't want to talk about network solids. So I'm just going to draw this little line over here because I want to recap molecule polarity really quick. All right, so when you have a molecule and you're asked if it's polar or nonpolar, this is not about which elements are getting together. This all has to do with the shape of a molecule. So in chemistry and biology both, the shape of a chemical structure is going to be the most important thing that's going to determine physical, chemical, and biological properties. So it's all about the shape. And then shape is either going to be either symmetrical, symmetrical, or asymmetrical. And then distribution of charge. So distribution of charge. So if the charge is equally distributed across the whole molecule, you have yourself a nonpolar molecule. And so I like to remember this as SNAP molecules together, which stands for symmetrical, is nonpolar, right? Because Polar means different, not different. So the symmetry of the molecule is not different, so it's going to be symmetrical. And if I have asymmetrical, is going to be polar, right? Because asymmetrical means different. If you draw some lines of symmetry, there's something different on either side of your line of symmetry that makes the molecule polar. And this whole molecule polarity thing, this is all going to lead us to our intermolecular forces, or sometimes we refer to them as intermolecular attractions, right? So we have those partial charges, right? Polar and polar molecules. And then we have our strongest, which is the hydrogen bonding. All right, so that's a pretty solid recap. And that's just a very brief set of notes, right? You really need to be able to think and apply in this unit. And it all comes down to practice and whether or not you're really, trying to focus on, and the ability to separate the word polar and nonpolar when we're referring to bonds, or whether we're referring to molecules, right? Because we're using the same terms, but in two different contexts, which we do all the time in the English language. Nobody has a problem with it. But when we throw it into science, all of a sudden, it's a little bit more challenging. But remember, polar means different. Nonpolar means the same. So if we're talking about a bond, it's who's getting together, the elements, polar and nonpolar. Two of the same nonmetals, two different nonmetals. And if we're talking about the molecule, it's all about the shape of the molecule, right? Because the molecules, when you put it all together, not just what two are together, but the whole shape and distribution of the charge. And then that's where we use the symmetrical, nonpolar, asymmetrical, polar. All right, so fast forward, rewind, go back, watch this video again, seek out more videos, ask questions in class. All right, and until we see each other again in our next video. Thank you.